Hi students, this is the third lecture series on the subject Operating System Design Module 1 for MTech students. I'm Seema Safar, Assistant Professor, Department of Computer Science and Engineering, Rajagiri School of Engineering and Technology. The content that will be concentrated on includes the introduction to system concepts, kernel data structures, and finally system administration. Let's start the session. Now let's begin the first topic, Introduction to System Concepts. So as we're dealing with files here, the first thing that we'll be discussing is on the inodes. What do you mean by an inode? Before that, you should know what is a file. You know what is a file, right? Now the internal representation of a file is usually given by an inode. Inode usually contains a description of the disk layout of the file data and other informations like file owner, access permissions, and the access time. When a process refers to a file by name, the kernel passes the file name one component at a time. It checks that the process has the permission to search the directories in the path and eventually retrieves the inode for the file. Hope you got the importance of inode for a file. So every file will be having an inode and each name is called a link. Now inodes are usually stored in a file system, but the kernel reads them into an in-core inode table when manipulating the files. The kernel contains two other data structures which are called as file table and user descriptor table. The file table is a global kernel structure, but the user file descriptor table is allocated per process. So each process will be having a user file descriptor table. So when a process opens or creates a file, the kernel allocates an entry from each table corresponding to that file's inode. Alright, so entries in the three structures, that is the user file descriptor table, file table, and inode, they will be maintaining the state of the file and the user's access to it. Now, this is a picture which depicts the file descriptors, file table, and the inode table. Now, this picture is taken from your reference textbook. Now, here the file table keeps track of the byte offset in the file where the user's next read or write will start. And the access, it also keeps track of the access rights which is allowed for the opening process. And the user descriptor table identifies all open files for a process. Now the kernel returns a file descriptor for the open and create system calls, which is an index into the user file descriptor table. Now Unix system keeps regular files and directories on block devices such as tapes or disks. They'll be usually keeping it on tapes or disks. And file system consists of a sequence of logical blocks. Each will be containing 512 or 1024 or 2048 or any convenient multiples of 512 bytes depending on the system implementation. Now in this figure, you can see a file system layout. A file system has the following structure as shown in the, as you can see in the screen right now. So it has a boot block, a super block, an inode list, and a data block. What do you mean by boot block? What is the responsibility of boot block? Now boot block will be occupying the beginning of a file system. It typically it is found in the first sector, and it may contain the bootstrap code that is read into the machine to boot or initialize the operating system. So if you want your operating system to be initialized, there should be a boot block which includes all the codes related to that. Then we have a super block which describes the state of a file system, which means how large the file is, how many files it can store, where to find the free space on the files, and so on and so forth. Then we have an inode list, which is a list of inodes that follows the super block in the file system. Administrators will be specifying the size of the inode list when they are configuring the file system. Then we have data blocks. Data blocks start at the end of the inode list and they contain file data and administrative data. An allocated data block can belong to one and only one file in the file system. Moving on to the processes, which is again another concept in system concept. A process is basically an execution of a program and it contains a pattern of bytes that the CPU interrupts as machine instructions, data, and a stack. Now they communicate with each other with the help of system calls. How do you create a process in Unix systems? By making use of fork system call, right? And the process that invoked in that has invoked the fork system call is the parent process, and the newly created process is the child process. So every process is going to have one parent process, but a process can have many child processes. Now, this figure depicts data structures for processes. Now, every process has an entry in kernel process table. Here you can see a process table where every process will be having a kernel process table, which will be including all information of the process. And then it will be having a per process, every process will be having a region table as well. Per process region table and then a region table. A region is basically a contiguous area of a process address space such as text, data, or stack. So region table entries will be describing the attributes of the region, such as whether it contains text or data, whether it is shared or private, and where the data on the region is located in the memory. Now moving on to another concept, which is context of a process. The context of a process is defined by its text, by the value of its global user variables and data structures, the value of the machine registers it uses, the value stored in its process table slot and U area, and the contents of its user and kernel stacks. While you're doing a context switching, the kernel will be saving the current information and it will be switching back to the first so that it can later on switch back to the first process and resume its execution. Normally, a process will be in any one of these states. This you might have studied during your graduate days. The lifetime of a process can be divided into a set of states, as you can see in the figure. The figure is taken from your reference textbook and the reference is attached in a slide at the end. The process states are: when you create a process, the process is currently executing in user mode. Here it is, you can see 4 circles. 1 is user running, 2 is kernel running, 3 is ready to run state, and 4 is asleep. The process is currently executing in user mode, and when the process is in state 2, it is executing in kernel mode. And in state 3, the process is not executing, but it is ready to run as soon as the scheduler chooses it. Many processes may be in this state, and the scheduling algorithm determines which one will be executed later. Now the 4th state denotes the process which is sleeping. A process puts itself to sleep when it can no longer continue executing, such as when it is waiting for an input-output operation to complete. And this is a state transition diagram which depicts the flow of the processes when they are in each of the states. Now usually a state transition diagram is a directed graph whose nodes will be representing the states a process can enter and whose edges represent the events that cause a process to move from one state to another state. Hope you understood this. Now let's discuss about kernel data structures. Most kernel data structures occupy fixed size table rather than dynamically allocated spaces. What is the advantage of this approach? Is that It is very simple. Kernel code is very simple, but it limits the number of entries for a data structure to the number that was originally configured when generating the system. Okay, that is the only problem. If during operation of the system, the kernel should, if it runs out of entries for a data structure, it is not possible to allocate space for new entries dynamically, but it will be reporting an error to the requested user. Now let's discuss about the last topic, system administration. Administrative processes are loosely classified as those processes that do various functions for the general welfare of the user community. So it includes functionalities like disk formatting, creation of new file systems, repairing of damaged file systems, kernel debugging, and etc. etc. If you see it conceptual wise, there's no difference between administrative processes and user processes. They basically use the same set of system calls available to the general community, but they are distinguished from general user processes only in the rights and privileges they are allowed. For example, a file permission mode may allow administrative processes to manipulate files. Okay. Internally, the kernel distinguishes a special user called the super user who is given special privileges. Now, a user may become a super user by going through a login password sequence or by executing special programs. So, in short, we can say that the kernel does not recognize a separate class of administrative processes. By this, we come to the end of this session. These are the reference textbooks for this session. Thank you.